We've talked a lot about antenna metrics. How do we describe the performance of an antenna and how do we measure it? But antennas are always part of a system. And for right now, what we're going to focus on is communication systems. And in a communication system, what matters is the ratio of the power received to the power transmitted. So how do we figure that out? The first key ingredient is something called the effective aperture of the receive antenna. You'll see these abbreviations a lot today. RX means receive, and TX means transmit. Transmit with a T. Now, effective aperture is sometimes effective aperture is sometimes also called effective area, or receiving cross-section. But what it tells you is the amount of intercepted power by the receive antenna. So what you get is that the intercepted power at the receive antenna is equal to the incident power density times that antenna's effective area. Now, not all of the intercepted power actually arrives at the receiver because there are efficiencies that need to be dealt with and matching concerns, but the intercepted power is the power that makes it from the air into the receive antenna. So, what is the effective area of an antenna? It's related to its directivity because we talked before about how an antenna's transmit and receive properties are the same. So the effective area of an antenna is equal to lambda squared times its directivity, which remember is a function of angle, divided by 4 pi. Here's how we would apply that, and here is also how we arrive at an expression that relates the receive power to the transmit power, which is what we care about. Now, first of all, we said that the intercepted power at the receiver is equal to the incident power density times the receiver effective area. Cool, but how do we find out what the incident power density is? The incident power density is going to be, well, first we've got the transmit power. It's proportional to transmit power. And then we've got that. It's got to be divided by 4 pi r squared because of our spherical propagation situation. And then we've got to multiply that by the gain of the transmit antenna. Now these angles refer to, I'm going to give them a little theta t and a phi t. So that is the direction toward the receiver antenna from the transmitter's point of view. So that gets us our incident power density. We could also write this if we wanted to split out the gain into its efficiency and directivity. We could write it as PT xi t directivity over 4 pi r squared. That would be fine too. So then, with that in mind, we know that the intercepted power at the receiver is equal to this incident power density, so PTX times the gain in the direction of the receiver divided by 4 pi r squared times the effective area of the antenna, which is lambda squared over 4 pi times the directivity of the receive antenna when looking in the direction of the transmitter. But, like I said, the intercepted power is not the power that makes it to the receiver, because again, we have an efficiency to deal with. So then we need to say that the power of the receiver is equal to the transmit power times the gain of the transmitter over 4 pi r squared times lambda squared over 4 pi times the directivity of the receiver times the efficiency, of the receiver. Now this could be collapsed down into the gain of the receiver. That would be fine too. But I wanted to leave lambda squared times directivity over 4 pi because that's effective area. So you could write this as S incident times effective area times efficiency of the receiver. Or you could write it all out in terms of its component parts. And if you move the transmit power over to the left-hand side, you get the gain of the transmitter times the gain of the receiver times lambda squared divided by 4 pi r with that whole quantity squared. Now I've swallowed up the receiver efficiency into the receiver gain, as you know. And this is the Friis transmission equation. Which describes how much power you're going to get at the receiver of your communication link based on the gains of the two antennas and the distance between them and the wavelength. So that is a really important tool if you're designing a communication system. It helps you decide what exactly do we need out of these two antennas and what are the trade-offs. A lot of the time, the transmitter is a fixed base station, especially these days, and you can have that be really expensive and really large, and it doesn't have to move or be lightweight or be carried by humans, and you can have engineers to maintain it. And then the receiver might be a handheld, small consumer device that can be a lot cheaper but has to be a lot smaller, and it has to be battery powered, so the gain that you're going to get out of the receiver isn't very much. So based on that, this is where you get to make those sorts of design trade-offs. Next time, I'm going to talk about noise and how you decide exactly how much receive power do you really need.